everyone, this is Miss List, and we are continuing our Unit 6 with an intro to enthalpy of a reaction. So hopefully you have done some experiments in chemistry and you've noticed that there are some reactions that will release energy and it gets hot, and you'll have some reactions where it absorbs energy and the reaction gets cold. Well, that is called the enthalpy of a reaction, and that is often written as delta H of the Rxn. There are two ways this gets represented to us in chemical reactions. The first way is by writing it off to the right of the reaction in question. So here we have nitrogen gas plus oxygen gas goes to 2NO gas. And off to the right, we have plus 180 kilojoules per mole. The sign written as positive tells me this is an endothermic reaction. Energy needs to be put into the system in order for it to go. If the sign was negative, that would indicate that it's exothermic. The other way that sometimes we see it represented is actually written as a reactant or product. So in this second example, we see 180 kilojoules actually written as a reactant with nitrogen and oxygen, and that's because it's endothermic. If it were exothermic, we would see that written on the product side. I will tell you that this first example is typically the way we see it represented by the College Board. This section is to just introduce you to the concept of the heat of the reaction and to do some examples where we multiply by moles and mole ratios. Example A says how much heat is required to react 2.4 moles of nitrogen with excess O2. It's nice that they tell us oxygen is in excess because we always want to do our calculations based off the limiting reactant. So them telling us that oxygen's in excess, that means that the is going to get used up completely. I can simply take the 2.4 moles and I know that it is 1 mole and it is going to require 180 kilojoules. So all I am doing is multiplying 2.4 times 180. If we do that, we get 430, and that label is going to be simply in kilojoules. This is going to be, remember, an endothermic reaction. This is energy that needs to be put in to make this reaction go. On the next one, it says if 25 kilojoules of heat was absorbed by the reaction, how many moles of NO were produced? For this reaction, I'm going to start actually with the 25 kilojoules. And I know that it is 180 kilojoules per 1 mole of the reaction. Well, for every 1 mole of the reaction, because this is based off of NO, if I go up and look at my equation, NO has a coefficient of 2. So I need to account for that in my chemical equation. I didn't do that on part A because it is a 1-to-1 mole ratio for both of my reactants. But since this one is asking how many moles of NO, which is a product, is produced, and our product has a coefficient, we need to account for that in our calculation. So I'm going to take 25 times 2, which is 50, and then 50 divided by 180, and I get 0.28 moles of NO were produced. Our final example is where it's the same idea that we have been exploring in our first two examples. The difference is that they don't tell me from the jump who is my limiting reactant. So I need to figure that out first. If I take 7.25 moles, and this is for the H2S, I know for every 2 moles of H2S, and then I'm just going to pick one of the products, I can make 2 moles of SO2. So that is going to be the same amount because they have the same coefficient. For my other reactant, that is the oxygen gas, I have 9.34 moles. And it is not an equal mole ratio. It's 3 moles of oxygen to 2 moles of SO2. So for this one, I actually get 6.23 moles of SO2. So by doing that quick calculation, it tells me that H2S is actually going to be my excess, which means I need to base off all my calculations off of oxygen being the limiting reactant here. I know that my limiting reactant is going to get used up first, and the maximum amount of SO2 it can make is 2 moles. From here, I know that it is 2 moles of SO2 for 1 mole of the reaction. So SO2 gets canceled, and then for every 1 mole of the reaction, it releases 1120 kilojoules. So I'm going to take 6.23 times negative 1120, and then I'm actually going to divide that by 2, and I get 3485. Again, that being negative because energy is being released. We will be talking about more specifics in the heat of reaction world over the next few sections, but the take-home points is how it gets shown in a chemical reaction. Usually, the way it's shown most frequently is here in our second example, where we've got a chemical reaction and it's written off to the side. Remember, our sign tells us whether it's endothermic or exothermic. Because this one's negative, that tells me it's exothermic. And then the second take-home point is that we always base it off our limiting reactant. So if we're not sure what the limiting reactant in the equation is, we need to find it. And then the third take-home point is that we always will adjust based on the mole ratio. And that's what we've been doing in these last few examples. All right, my friends, thank you for joining, and we have 3 sections left. Next up is section 6.7.